For any finite set S, let cardinality S denote the number of elements in S. Find the number of ordered pairs A and B such that A and B are not necessarily distinct subsets of 1, 2, 3, 4, 5 that satisfy cardinality of A times cardinality of B is equal to the cardinality of the intersection of A and B times the cardinality of the union of A and B. Interesting. Okay, so we're starting with the set of, well, a set of 5 elements is really what's important here. The sets A and B are not necessarily distinct. So, of course, we need the number of ordered pairs. Let's just, in fact, call this S. So A and B are subsets of S, and we want cardinality of A times cardinality of B equal to the cardinality of the intersection times the cardinality of the union. Now, if A equals B, then obviously the cardinality of A is equal to cardinality of B, but this is also equal to the cardinality of A intersect B and the cardinality of A union B, because all of these sets will in fact be the same. So any two subsets of this where A equal B will work. But wow, we have quite a interesting problem here. Let's also note the cardinality of S is 32. Right, this is 2 to the power of 5. I suppose one way of doing this is the cardinality of S isn't 2 to the 5. The cardinality of the power set of S, the number of subsets of S is 2 to the 5. Oh, sorry for freaking some of you out so quickly. Obviously, the cardinality of S is 5. So maybe, like, do we want to look at, like, so what is the total number of ordered pairs A and B that are subsets of S? It's going to be 32 squared, right? The maximum possible value of this of the answer here is 32 squared, which is 1024, because that's the total number of ordered pairs. Okay. I guess maybe there's going to be something about, maybe we look at factors of A and B, right? Cardinality of A is a number between 0 and 5. The cardinality of B is a number between 0 and 5. These are both numbers between 0 and 5. So, like, let's in fact consider cardinality of A is 0. So A is the null set. Then the equality is trivially satisfied because both sides will be 0, right? A intersect B will also be the null set. So this means there are if A is the empty set, then B can be anything sets B which work. And similarly, if B is 0, B is the null set. B is the null set. And there are 32 sets A which work. But of course we've double counted one. We've double counted. So including double counting null set, null set. I definitely don't want to iterate. Maybe what we can do is we can eliminate, like if we assume the cardinality of A is equal to 1, then maybe we can eliminate, okay. Yeah. I'm going to sort of keep exploring specific cases like this and see what kind of conclusions we can make. But if the combinatorial arrangements get completely out of hand, then I might have to stop this and think of another approach. But let's suppose cardinality A is equal to 1. Then we must have, in fact, let's suppose A is the singleton 1. We must have, okay, and let's also suppose the cardinality of B is not equal to 0, because that case is already covered up here. We must have 1 is also an element of B, otherwise the intersection has cardinality 0. But then, so if in this case, A intersect B is simply equal to A, and A union B is equal to B. So this means any B such that B is not equal to the null set and 1 in B works. And how many sets of that do we have? 2 to the 4 minus 1. Because we have the numbers 2 to 5. 2, 3, 4, 5. Any combination of those can work, except the one that's empty. And there are 5 original starting. Well, what is this? This is 15. Problem now is when I sort of flip the roles of the sets A and B, we're going to double count. Okay, so there are 5 times 15, which is equal to 75 pairs with cardinality A equals 1, cardinality B not equal to 0. Okay. Rather than exploring what happens when the cardinality of B is 1 and cardinality of A is non-zero, right? It's going to be a repeat of this argument. We just have to be careful not to double count certain combinations. I'm still kind of just trying to figure out what's going on here. Let's suppose the cardinality of A is equal to 2. And let's suppose the cardinality of B is equal to 1. Then we need B to be a subset of A. Maybe the way to do this so far, just about everything I've thought of has one set that is a subset of the other. So maybe what I should do is figure out whether this equation can ever hold where sets are not, where one is not a subset of the other. Where one is not a subset of the other. Is it possible that A is equal to 2 and B is equal to 3? So on the left-hand side is 6. But then, if one is not a subset of the other, this has to equal 1 or 0. And if it equals 1, then the union has to have cardinality 6, which is not possible. Okay, so let's say no subsets. We're only looking for cases that work where neither is a subset of the other. So this is not possible. And I mean this combination is not possible. So let's try A equal 2 and B equal 4. Then again, A intersect B must equal 1 or 0. Can't be 0 because we need the product to be 8. Ah. Yeah, this obviously, like, this can't hold. The we need to start looking at cardinalities where one of them is greater than 2. Okay, so if one is not a subset of the other, then it's not possible for one of them to have a cardinality of 2. Let's try cardinality of 3. And again, neither is a subset of the other. Well, this clearly means that the intersection and the union must both have cardinality 3, but that means, I'm talking, if A is equal to B, I consider that to be, I consider those to be subsets. So this can't work. What about A equal 3 and B equal 4? Then I have this is equal to 12. So I would need the union and intersection clearly they both also have to have cardinalities 3 and 4, but the union would then have to have a cardinality 4, meaning that A is a subset of B. So this can't work either. And that's all the cases, right? I guess the only one that's left is when they're both equal to 4. But if one is not a subset of the other, I have 16, then the union has to be 5, and this is a contradiction. Okay, so I think what this has shown is that it's not possible for this equation to hold if neither set is a subset of the other. Like if we don't have one set contained in the other, this can't work. Okay. But, hold on, did I say already that if A is, then if A is a subset of B, implies A intersect B is equal to A, and A union B is equal to B. And so this equation is trivially satisfied. Well, not trivially. This equation will be satisfied if one is a subset of the other. So what I need to do then is fix A, count subsets of A, and that will be the total number where B is count the subsets of A, and then so this will be, for a fixed A, count how many subsets of A there are. That's somewhat trivial based on the cardinality of A. And then add up over all possible subsets, all possible sets A. Then we have to do the inverse and count them up again and add them and subtract the double counts. Okay. So for fixed A, number of subsets of A is 2 to the cardinality of A. Okay. And so now what I want to do is add 2 to the cardinality of A as A ranges over all subsets of S. Okay. So I need to count how many sets are there of cardinality 0, how many are there of cardinality 1, how many of cardinality 2, and so on. This is going to be, these are like combinatorial coefficients, aren't there? Aren't they? So this is equal to 2 to the 0 plus 2 to the 1 times the number of subsets with cardinality 1, and that's 5, plus 2 squared times the number of subsets of cardinality 2, and that's 5 choose 2, plus 2 cubed times the number of subsets with cardinality 3, 5 choose 3, plus 2 to the 4 times 5 choose 4, plus 2 to the 5 times 5 choose 5, which is 1. Okay, and is this an easy thing to expand? 1 plus 10 plus 4 times 5 choose 2, I don't know, 5 factorial over 3 factorial 2 factorial plus 8 times 5 factorial over 3 factorial 2 factorial plus 16 times 5 plus 32. Okay. 11 plus 2 times 5 factorial over 3 factorial is 5 times 4, 20, plus 4 times 20, plus 16 times 5, 80, plus 32, $51 plus 160 plus 32, $51 plus 192, 143. So this is the number of ways of satisfying this where B is a subset of A. Okay. Now we multiply that by 2 because there are also 143 ways where where B is a subset of A, and 143 ways where A is a subset of B. So that gives us 286. And now let's subtract how many ways where A is equal to B. That's just the total number of subsets. That's like any subset, we can just, any subset of S, we take 2 copies of it. And that's 32. So by adding these together, we have double counted 32 ways. So I need 286 minus 32, which is 254. That's going to be my final answer. I will let you know if I'm incorrect. I hope I didn't skip over, like in this process all the way up here where I was trying to eliminate certain cases or figure out what's going on. I hope I didn't actually skip, I hope I didn't accidentally skip over a case which can be included and I've eliminated it. But based on my going through of all this stuff, I believe it's true that one of these sets must be a subset of the other. And so then it's just a case of enumerating over all possible ways of doing that. And I get 254. That was a cool problem. Yeah, certainly took a little bit of, I wouldn't quite say guess and checking, but a little bit of sort of wild exploration to try and figure out what is going on. Thanks for watching.